So now let's talk about topic modeling. So what's the problem we're trying to solve in topic modeling? We want to find topics in text, and there are two solutions to this problem. We can either go with supervised or unsupervised learning. So in supervised learning, which is a great solution, we annotate the text with topics, then we train a classifier, and then the classifier can tell us whether a document belongs in one particular topic or not. Well, the issue with this approach is that it's not easy to manually label thousands and thousands of documents. That's why in practice, most often we use unsupervised learning for topic modeling. And this is what we're going to talk about in this session. So there are two main techniques for topic modeling: latent delay allocation, or LDA for short, and non-negative matrix factorization. We'll start with LDA. So again, topic modeling is a bit like clustering for words. We've assumed that we have a predefined set of topics, let's say 5. An LDA is a probabilistic model that makes the following assumptions. Each topic is a distribution over words, each document is a mixture of those topics, and each word is drawn from one of those topics. So we have these topics that define distributions over words, and then each document belongs in different proportions to these topics, and the words are generated from those topics. Let me break this down a little bit. To repeat again, topics are distribution over words. So what this means is that we have every possible word in our corpus, let's say car, basketball, a circuit breaker, whatever. And for each topic, each word is assigned a probability. So some words are going to be more likely for some topics rather than other topics. The documents are described as a mixture of those topics. So maybe an article from BBC that talks about sports, but maybe it also talks a bit about some other matter. I don't know, maybe it relates to transfer of a football player. So you could say it also touches upon some words related to finance. It could belong with a 70% assignment to sports and 20% to finance and 10% to something else. So we have the words, and then we want to understand what these topic distributions look like and how each document is assigned to those topics. So in reality, however, we don't know anything about these probabilities. The only thing we know is the words. That's the only thing we observe. We only observe the documents and the words. And this is what LDA looks like as a graphical model. So we observe the words, which are in darker colors, as you can see in this image, and we don't observe anything else, and we have to infer it. So this is our goal. So given the documents, where the documents are expressed in words, we have to extract the topics and the goal distributions per document, and then for each document in the corpus, identify to what proportion it belongs to each topic. So again, our data in this case are the words in different documents, and we want to infer the rest. We want to infer the topic distributions and the distributions of the documents over the different topics. So a note here, in Bayesian statistics, the mathematical details can be quite advanced. However, it's important to revisit a few things here. So in Bayesian statistics, we assume that we have the prior, the likelihood, and the posterior distributions. So the likelihood is the evidence, is what our data tells us. The prior is the knowledge we have from the world before we observe any data, and then these two get combined in order to give us the posterior. So in Bayesian statistics, we have to define distributions for the prior and the likelihood. And there is this concept of conjugate distributions that make the math in our lives easier. Why? Because they follow a certain mathematical format which makes updating the posterior parameters easier. So in general, it is desirable to work with conjugate pairs, as we call them, prior likelihood pairs. So it will become apparent shortly why I'm saying all this. Another important note, the beta distribution, it's a distribution over the interval 0 to 1. So it has two parameters and many different shapes. And as you might have guessed, if you have this kind of distribution between 0 and 1, you can use it to express probabilities or proportions, pretty much anything that falls between this interval. So the beta distribution has a generalization to multiple dimensions, to an arbitrary number of variables, through the Dirichlet distribution. So the Dirichlet distribution can be distribution over proportions. Yeah, so you can have 10 different entities and you can say that yes, the first entity has a proportion of 50%, the second one 10%, etc. So I hope by now that you've seen where this is all going. So the multinomial distribution is another important distribution for LDA because it's a distribution over counts. So if, for example, you have a set of documents with words, you can use the multinomial distribution to express word counts. So we have all these different distributions and, you might feel a bit confused by now and you're like, okay, what does the name Dirichlet mean in the end of the day? So there was this mathematician, Johann Dirichlet, who came up with this generalization of the beta distribution, and the Dirichlet distribution is the conjugate prior to the multinomial distribution. So the multinomial distribution is needed in our probabilistic model, which we call LDA, because we want to express word counts. And because we're in a Bayesian setting, we need to use a prior for those counts. And as I explained earlier, the math gets easier if we use a conjugate prior. And this, for the multinomial distribution, is the Dirichlet distribution. So we have two things, a distribution over topics, and a topic is a distribution over words. So the Dirichlet distribution allows us to express a distribution over our topics, and the Dirichlet multinomial distribution allows us to express the count of words. Hence, the Dirichlet multinomial model is being used for LDA. Again, some of you might be more comfortable with maths and might want to delve deeper into the details. If you just want to use LDA, it's a good idea to know about some of those things, but you really don't have to fully understand the details, even though it is advisable. So LDA is a generative model. That's something very important. So you choose a number of words that a document will have, and then you choose a topic mixture according to this Dirichlet distribution over a set of topics. So if you remember, each document is going to be assigned in a soft way, a score, a proportion to which it belongs to the different topics. So we have three different topics. We could say that document 1 belongs, let's say, 90% to topic 1, 5% to topic 2, and 5% to topic 3. So this is expressed through the Dirichlet distribution. And because each topic is a distribution over words and each document is a distribution over topics, we can use this structure in order to generate words from this model and see how would a document that talks about sports would look like, or how would a document that talks about 50% about sports and 50% about finance, how would it look like? And then this model will generate words for us. So LDA is a probabilistic model, which means it has various parameters we need to estimate. Basically, complicated models essentially break down into complicated probability distributions, which we cannot analytically estimate. So this is where we have to use a Markov chain Monte Carlo, which is this sampling family of methods to use when the distributions that we're dealing with are way too complicated. So LDA is traditionally solved through Gibbs sampling, which is one of the oldest and most successful Markov chain Monte Carlo techniques, even though now there are many different ones and actually research constantly coming up with better and faster methods for sampling from complicated distributions. So through Gibbs sampling, we do the following. We start by assigning words randomly for each topic, and then we determine the probabilities of each topic given the rest of the data. We choose the most probable assignment of documents to topics, and then we iterate this process until the algorithm converges and the probability assignments of words to topics and documents to topics do not change. So why does LDA work? Well, LDA essentially trades off two goals. For each document, we want to allocate its words to as few topics as possible, and for each topic, we want to assign high probability to as few terms as possible. So the issue is that these two goals are at odds. Putting a document in a single topic makes point too hard because all the words in this topic must have high probability under this topic, and we've defined as goal 2 that only a few words should have high probability. On the other hand, if we put very few words in each topic, then point 1 is hard because in order to cover a document's words, then this document would have to be assigned to many topics. And we said that ideally we'd like one document to correspond to only one topic. So in the process of the algorithm trying to find a trade-off between these two goals, it finds this distinct cluster of words and these distinct topics, which are then assigned to the documents. And in practice, this works quite well. So here's an example. This is a collection of articles from the Science magazine over 10 years. We have 17,000 documents, 11 million words, 20,000 unique terms, and we create a 100-topic LDA model. And you can see here the most frequent words for each topic. So you can see that topic 1 talks about DNA, gene, and sequence, and topic 2 talks about protein, cell, and receptors. Topic 3 is talking about the water, the climate, etc. So LDA was very successful in finding the different kinds of topics. And you can see, for example, topic 20 talking about the neurons, the brain, and topic 7 talking about data. This is another very good demo of LDA. You should go on this link, which is provided in the additional resources section, in order to play around with this demo. This is LDA run on movie review data, and you can play around with the different parameters and see how the topic assignments change, and you can also see how the different topic assignments change and the differences between the topics and the relationships between them. So I'm not gonna stay too much on this. Just go ahead, have a play with it, and also try to answer the following questions. So feel free to pause the video here for a second to read through these questions and try to answer them by playing around with the demo. So there are some other methods for topic modeling. For example, latent semantic analysis or latent semantic indexing is a method that's essentially very similar to LDA. Non-negative matrix factorization is another method. And now we're going to talk a bit about non-negative matrix factorization, which achieves very similar results to LDA, but takes a different approach because it is a matrix decomposition method. So in matrix decomposition, we have a matrix for our data, and we want to break this matrix down into other matrices, which are going to capture these interrelationships between the rows and the columns that we want. So more specifically, we have this matrix A, which contains n rows and m columns. In our case, each row is a document and each column is a word and each cell is the frequency of this word in a document. So what we want to do is we want to find k clusters and we break this matrix into matrices. Matrix W has a dimension of n times k, where n is the total number of rows or the total number of data points and k is the total number of topics. And we call this matrix the basis vectors matrix. And then we have the coefficient matrix, which is of dimension k. We have k rows and m columns. And this determines the assignment of each document into a topic. So these coefficients are inferred through an iterative method such as gradient descent or expectation maximization. And the most common objective is essentially the squared error between the decomposed matrix and the original matrix. So just to explain what's happening here, this is not a probabilistic model. This is a matrix decomposition model. So it's a linear model. And we're trying to minimize what we call the reconstruction error. So we are breaking down a matrix in two matrices, and we accept that decomposition is not going to be perfect, but in the process of actually losing some information, we are able to reduce the original form of the matrix into different matrices which are a reduced version of the first. And they can capture the information we want, in this case topics, in a summarized form. So this optimization goal here is similar to the optimization goals that you're going to see for logistic regression or neural networks, again because this is a linear model. So we are no longer sampling from a probability distribution, we are just trying to optimize an error. And let's see how all this works through an example, because it might be a bit confusing so far. So let's say that we have this matrix here. This is the data matrix A, and this is the matrix that we want to break down in documents and topics. So we have different documents here, and we want to express here the occurrence of different words in the topics. So let's say we did some pre-processing, removing some words, maybe normalizing the frequencies. And you can see that, for example, for document 2, these are the words that occur most often: bank, money, finance, and TV. For document 5, it's like document 2, bank, finance, and TV. Yeah, whereas for document 4, the most common words are TV, show, and actor. So now we want to decompose these previous metrics in two matrices: the matrix W and the matrix H, which when multiplied, they will give us back A. And we want this decomposition to be done in a way so that when we try to get back A from W and H, we will get a version of A that's as accurate as possible, because there's going to be some error involved in this. The reconstruction will not be perfect. So what the basis vectors look like is like this. We have a set of columns which are equal to the number of topics, and a set of rows which are equal to the number of words, and each word is assigned to a topic. So you can see that bank, let's say, and finance are assigned a high score. It's not a probability in this case, in topic 3. And words sports club and football are assigned a high score for topic 2, etc. So you have 3 topics here in columns and all the words as the rows. And then in the coefficients matrix H, what we have is the documents as the rows and the topics as the columns. And then this matrix expresses the assignment of a document to each topic. So we can get from the basis vectors the topics and see what they express, which words are the most important for those topics. And then through the coefficients matrix, we can get the different memberships of those documents over the topics. So in terms of implementation, non-negative matrix factorization is similar to LDA. You're going to get pretty similar results with both of them. So it's more of a matter of trying out both and figuring out what works best. And these kind of techniques can also be applied to other fields, such as computer vision. This link is provided in the additional resources session for you to check out.